John is handing out the blank sample questions. Attached to that, there are the spring problems. In the slideshow here, there'll be intermittent notes, so please don't do that, Ryan. I need my screen for the next time around. Okay? So yeah, let's begin, and hopefully we can get done
What do you need
in time. Well, the sample questions are sort of embedded in the notes. So those samples right there are embedded inside this. So if you want to have a loose leaf going at the same time as those.
So we got a lot of.
Okay. Usually I separate these 2 days, but just given what has to happen tomorrow, this will be the better use of our time, and we won't waste another period. Okay, so briefly here, we're going to talk about Hooke's Law. Don't write any of this down. There are springs that you can stretch, that are designed to be stretched, and there are strings that are designed to be compressed, right? For example, the springs on a car, they're already sort of expanded and they're designed to be compressed and be a shock absorber, right? In click pens, they are expanded and they're designed to be pushed. There's other ones like those ones that are designed to be stretched. And then there's ones that really go up and down. The general idea is that all springs follow the same law. It doesn't matter what kind of spring it is. Pull apart or a stretch one. Or compress kind of thing. Doesn't matter what kind it is. There's Robert Hooke. Did that look like you when you were doing the Hooke's Law lab today? Probably not so much. Hooke's Law relates the amount of force F that you exert on a spring to the distance x that the spring is either stretched or compressed. So it's a relationship between the amount of force which you used a weight to come up with the force. It's the easiest thing we can do because we just multiply by 9.8 and we get a perfect amount of force. We know how much force it is. We don't have to use a scale. So it's relating the amount of force F to x. You don't need to write that down. That's just, I'm telling you, that's Hooke's Law. Did your graph look like this? It should have been, for the most part, linear. Which gives you, and I'll give you an answer for tomorrow or for yesterday or for today, I guess. That's the proportionality statement. F is proportional to x. The greater the force, the greater the stretch, right? It's not a curvy one. If it was a curvy one, it might be F is proportional to x squared or what have you. Could be x cubed too, I suppose. It gives us the equation F equals kx. What's the k? Remember from uniform circular motion? It's just some constant, right? This is not an equation, this is proportionality. So the k is the number that makes it work. Much like if you've got circumference of a circle, it's proportional to the diameter, right? The bigger the diameter of a circle, the greater the circumference. And what's the number that makes it work? Pi. Okay, that's the proportionality constant. Here we get a proportionality constant. Do all circles have the same proportionality constant? Yes, 3.14. Do all springs have the same spring constant? Are some springs easier to pull than others? Absolutely. So that implies that every spring has its own spring constant. Did your springs have different constants? Slightly different, right? They're kind of close, but you should have gotten. You're supposed to graph them on the same axis. Okay, so I showed that group. I showed you guys, right? So what you should get is two graphs on the same line. What is the spring constant? Well, this is the x here, and this is the f, right? Okay, and so the m, the slope value, is equal to your spring constant, which you're going to find by finding the slope of your trend line. Okay? So Hooke's Law says the force exerted upon a spring is directly proportional to the amount the spring is stretched or compressed. It's a direct relationship. And the constant of proportionality, the constant k, is called the spring constant. Every spring has its own. In this particular case, the one that's coming up here, or the one that I just graphed, the slope of the line is 35 newtons per meter. You're going to come up with a different spring constant, not 35. Okay, but it's always measured in newtons per meter. How much force it requires to pull it 1 meter. Now, you might say, Mr. Bennett, I can't stretch this spring a meter. What will happen if I stretch it a meter? Actually, I might be able to, right? That's pretty close to meter base, yeah. Some springs you can't. Think about the spring of a pen. Right, that little one's about this long, you know? Could you stretch out a meter? Not even a meter long to begin with the wire, right? But it still has a spring constant that's measured in newtons per meter. The spring constant gives the amount of force required to stretch the spring a distance of 1 meter, if you could. Right? If you can only stretch it half a meter, well then it would be 17.5 newtons, right? That kind of thing. Okay. Do you have sample questions in front of you? This is sample number 1. When a 6 kilogram mass is attached to a vertical spring, the spring stretches or compresses a distance of 40 centimeters. Find the spring constant. Hopefully you recognize right away that this is per meter, and so step 1 would be to change that 40 centimeters to meters. Right? Which is right there. How much weight force is there? Well, it's 6 kilograms. Six times 9.8, 58.8 newtons is the applying force. The distance is 0.4 meters. And so the spring constant for this spring is 147 newton per meter. The numbers tend to be in that sort of range kind of thing, because stretching a spring a whole meter usually is quite a distance. So the answer here is 147. Pretty straightforward, right? No problems? Okay. What about potential energy? Do springs contain potential energy? Yes. Consider the amount of work you do on a spring with a 200 newton per meter constant. Work is force times distance. The force exerted is found by using Hooke's law. So I'm going to replace this F with Kx. Distance is another distance, right? Another x. X and distance are going to be the same thing. So suppose this data is found right here. These need to clean up here. What's the average force exerted here? 0 meters needs 0 newtons. 0.1 meters needs 20 newtons. What's the average force here? 0, right? We started with 0, and as we get to the end, 100. So the average is 50. 100 divided by 2, right? 0 plus 100 divided by 2. The average force is 50 newtons. How much work did we do? Average 50 times 0.5. We did 25 newton meters, or 25 joules of work on this spring when we stretched it from 0 all the way to 0.5, right? And as I pulled, it got harder and harder to pull, right? So the amount of work that I did was 25 joules. Where did that 25 joules of work go? When I stretched the spring. I suppose there is some kinetic because it is moving, but eventually it's not kinetic, it's potential, spring potential, right? Because if I let go, then it goes back to kinetic. So yes, it's converted, that 25 joules is converted to spring energy, spring potential energy. Is there another way to calculate work on the spring? You guys have seen this kind of thing before. Work done is W equals FD. If it's a constant force, this isn't a constant force though. If it was a constant force, it'd be a straight line graph, wouldn't it? FD, what would this be? What would that area under the graph be equal to?
Work.
It'd be equal to work. Force times distance. The area under the graph would be work. But it's not a straight line. Right? But is it the same? Area is going to be the work here. Even though the force is increasing, the area under the graph, the area under a force distance graph is work. bottom, put it away and listen. There it is there, right? So how much work is done here? 1/2 the base is from 0 to 0.5, the height is 100, 25 joules of work. The same number that I came up with when I did it this way, right? How did I do it this way? I found the average force, and I multiplied by the distance. I got 25 joules of work. When I do it...
So do you have to find the average of it?
No, I'm just showing you how the relationship works, right? That's all.
Okay, so,
I'm going to show you how to do it, right? I'm just giving you the theory behind it, right? I'm giving you the theory. And really, if you stop and think about it, I got area of this triangle, 1/2 the base times the height. Well, didn't I just take 100 and divide by 2? Isn't that all I did? Right? So it's no wonder that it works the same, right? Imagine, if you will, at the line at 50. Like so, all I did is take this amount right here, and it's right there, right? Just flip it over, and there's my area, like that, kind of thing. Okay, algebraically. Area, 1/2 the base times the height. The base is the distance. The height is the force exerted. So that's 1/2 x. The force exerted is kx, and so what am I going to end up with a formula? 1/2 kx squared. Potential spring energy, US is the amount of potential energy stored in the spring, and that's equal to 1/2 kx squared. That's the formula. The potential spring energy is 1/2 kx squared. The potential spring energy is 1/2 kx squared. What does the US stand for? Potential spring energy. What 1/2 is 1/2. What does the K stand for? Spring constant. What does the X stand for? Distance stretched or compressed. That's the X.
and that is,
That's the formula for potential spring energy. And again, that's true for something that's stretched or compressed. What about a bungee cord? Anybody ever bungee jump that left out of the mall or anything? No? Yeah, you have? Do they make you stand on a scale and weigh first? How come? You know why? Yeah. They know what spring constant to use, and they want to get you just touching the water, right? And so with your mass, if you have 60 kilograms of mass and you're way up there, you have a certain amount of potential energy that's converted to kinetic as you fall, and then what does that have to be converted to? Potential spring energy. So if you weigh more than what you say, what's going to happen? You're going to have more potential energy, which is going to be converted to spring energy, which means you might put your head at the bottom. Cool. Over there. So yeah, it's important that you not lie about your mass when you go bungee jumping. I'm sure they actually measure you. They don't just say, how much do you weigh? Yeah. Okay. This is really sample 2, I think, right? I watched someone jump there. I was like, holy moly, are they serious? They're going way... Is West Edmonton Mall, Heather? You're braver than I am. Was it scary? No? No? I don't even like ladders. I don't even like watching people climb up high. If you do 24 joules of work in compressing a spring whose constant is 80 newtons per meter, how far is the spring compressed? What am I solving for here? Solving for x, right? US is 1/2 kx squared. What's the 24? That's the US, 1/2. The k is 80. Solve for x, right? Right? it around? Yeah? Do you want to try this one on your own?
Yeah.
You got lots of space if you make a mistake, right?
Yeah.
Okay, give it a whirl. It's backwards.
Oh, yeah. Yeah, but don't know how to get to work from.
Well, work is equal to the potential energy of the spring.
It's equal to you guys.
Actually, work is the change in. We should go back a little bit here.
Yeah.
I never actually wrote it here. I should put it in here somewhere. Well, maybe it's coming up right here. But work is the change in potential energy. Like, if it's got zero potential energy, it's just loose, right? And then I stretch it, well, its potential energy is the change. What if it's already got some? And then I stretch it more.
Well, that's what it's asking.
That's what it's asking.
Okay, well,
Okay, so how much does it have? The work done is the potential spring energy gained, right? So how much does it have to begin with?
oh,
USI, potential spring energy initial. 1/2 of 200 times 0.1 squared. It has 1 joule already to begin with. How much does it have when you are done, when it's at compressed at 0.4? 16. 1/2 of 200 times 0.4 squared is only 16.
I was thinking of that.
We're going to get to that. That's not 0.6. That'll be 0.3. Right? Okay? So if it had 1 joule of spring energy before, and now it's got 16, how much work did you do? You did 15, right? You added 15 joules of potential energy. Where did that extra 15 come from? You did work. The 15 joules comes from work. Now, this question comes up every semester. Can't you just go 1/2 200 0.3? Can you? No. Okay? Because the work is the change in potential energy. So you can't just go, if you go 0.3, you're going to have 1/2 of 200 of 0.3 squared. That's 100 times 0.09. You're only going to have 9 joules. Okay? If I go from 0 to 0.3, I'm going to do 9 joules. But because I need that last extra 10 centimeters, needs more force. Between 30 and 40 is a greater amount of force than 20 to 30. So I have to do more work. Okay? So you have to do it this way. You have to find the difference.
Well, why are we adding them? Or do you subtract? Oh, sorry.
Subtract. Right? The work done, this is the key idea here. The work done is the potential energy gain. So you have to figure out how much did it end with, how much does it start with, and subtract. Good?
How do you compress something bigger?
How do you what?
As being compressed to 1, or 0.1 meter.
Well,
What work have
it's
to do to compress to
yeah.
0.4?
So think about like a car spring that's like this, right?
Yeah.
It's unwound, right? And you compress it that far,
Yeah.
right? And then you compress it even more. It's not this kind of spring. This kind of spring you pull apart, right?
So the thing is, it doesn't, like the way it's worded, it should have worked in stretch because compressed doesn't make any sense.
Yeah, fair enough.
Like that,
Like here it is here. It's all stretched out, right?
So is it the amount on like the out? Like is it the amount that it's compressed? Is what you're measuring?
Yeah.
Oh.
Yeah, the amount that it's compressed. Yeah.
So you'd measure from like say like you were compressing it
Well, I thought
over
you-
here, you'd measure this over here.
Yeah, like a bumper.
I thought you were talking like
The size of the spring.
No. Oh, no. Good point. No. Think about a bumper that's like maybe, I don't know, 1/2 meter long, right? Like the bottom of like a roller coaster or something, some big shock absorber, right? And it gets compressed like this, and then even farther. And you're measuring the amount of compression.
Say that it's a meter and went like that, you wouldn't say.
It's now 90.
You wouldn't, yeah, but you would say it was compressed 0.1.
Yes, not 90, right. Gotcha. I should have a picture here. Or just make it. Yep, I understand your difficulty. Okay, what about things bouncing on springs? This is sort of putting it all together because you've got potential, you've got kinetic, you got spring, it's all together. I hope I can get done here. Consider a mass colliding with a spring as shown. Okay, so here's this mass. This is my poor drawing of a spring. Okay, imagine that's a spring. And this is a solid object, and this little white guy here, little white box, is bumping into it, okay? Before the collision, all the energy is kinetic. During the collision, the kinetic energy of the mass decreases as it does work to compress the spring. Just like your car crumples, right, when you hit something. That's why you've got that crumple zone. It's meant to do that. Originally, cars were made very rigid. They thought that was safe. They were completely wrong because there's no energy absorption. Here, all that kinetic energy goes into crumpling it, right? Okay? This energy must be conserved. Again, as the other day, ET, total energy, is kinetic energy plus potential, but now the potential is not mgh. Now the potential is 1/2 kx squared. And the total of those two must remain the same. I know you're going to struggle with these, and we probably don't have time to do a very good job of this.
So we're gonna,
You're going to get a work rate. That's what you just saw. I'm speeding through this here. At the end of the collision, all of the energy is transferred to the potential energy of the spring. It's analogous, identical to when the object is launched. Here you have nothing but kinetic. Here you have all potential, right, at the top. So EKI, initial kinetic energy, 1/2 mv squared, is equal to USF, final spring potential energy, 1/2 kx squared. Those two are equal to each other in this type of collision. Here's the sample. Is this what you have? I hope so. I know I'm really scrambling here. How about I just do this? Is that a good idea? It's up to you. Do you want me to go through it? I'm not here tomorrow. That's why.